Today's talk is, like it was mentioned, keeping your state at bay. You might have read the session abstract. But in the end, we're working with Kafka and stream processing, which means essentially like an ever-flowing state of events. And in the context of working with stateful Kafka streams, that could also mean an ever-growing state of events where state stores essentially would just grow infinitely if you're not working with windowing or have any techniques or things in place to actually limit the infinite growth if you have use cases where you do not need all your data for all the time. So let's get started. My name is Hartmut Armbruster. I'm a software engineer. I've been an independent consultant for more than 16 years. I like to design, be hands-on and design efficient, robust, and fit-for-purpose architecture, and which also kind of co-aligns with the nature of this talk to also manage state and avoid moving and keeping data that's actually no longer required or needed. So as for today's agenda, we will deep dive a bit further into the actual subject, what this is about, limiting store sizes, and what's the actual use case. I will address key challenges of growing state and why we would want to avoid that if there's no need for the actual data. And then go further into what are the actual requirements for data exploration. And then the main section is to actually present actually 8 patterns how you could achieve something like TTL with Kafka Streams, since it's not supported out of the box. And last but not least, also if you have to deal with very large state, some of the patterns might not work, or there's more patterns I will present and ways to deal with that. And close with a small summary of all the patterns. So, limiting state store sizes. Like most of the time, everything stream processing is everything around time. So time is the essence. And actually for certain use cases, data loses the relevance over time. And there are certain practices like working with Windows where you keep focus on recent data or on specific frames of data you want to work with and aggregate, for example. But they cannot fulfill all sorts of requirements. So, but usually if data loses relevance, outdated events are evicted. It's the nature of TTL, time to live. But here's the challenge. Many use cases have dynamic expiry requirements on data. So it's based on predicates and not just based on time. Like an example where you can use windowing is in analytics, or if you would have meter readings of temperature, you want like an average temperature over 1 hour, something like that. You can work with everything out of the box using session windows, hopping windows, tumbling windows. But as an example from the actual abstract I put in for the talk, a good example is the context of a parcel delivery service where you would want to have a tracking history. Everyone knows has ordered things online before. And essentially, this dynamic expiry in this case applies in the sort of, if it's same-day delivery, the completion of a parcel delivery can take anything from hours to even weeks if it's like a low-priority international delivery going through customs, or it might not even be delivered and then returned all the way back across the globe. So, once a delivery is completed, you could essentially the state around that, the tracking history, becomes immutable, and there will be no further events on the data. So you could essentially just archive that, stream it to a database, and keep it for long-term storage. Even then, you might not want or need to keep it for years, but maybe for a few months to access the tracking data. But you certainly won't need that in your actual stream processing applications which, for example, notifies the user if there's progress in your delivery. And this is one of the examples. Another good example, many of you might have traveled by plane to this event. If you go to the airport, the first thing you do is you look at the departure board. Another good example, beautiful kind of stream processing example to aggregate the next flights. There's updates on the gate you need to go to when it's boarding time or if the flight might be canceled or delayed. So this is also where data, after the plane has departed, maybe with a bit of buffer, it loses relevance, and you would not want to keep all the flights for the past months or years if everything you need to do is to display the next flights over the next couple of hours. So this is what I'm talking about today. And let's move on to key challenges of growing state if we would just infinitely grow our state and not purge and do such a TTL. Obviously, resource usage. So the bigger the state, you need to store the data on disk or in memory, so higher the cost. Along with that comes scaling issues. So we all know rebalancing, if you need to scale out or scale down, you need to move state. Bigger the state, the higher or the longer it will take to move all of that. And again, network costs. There's a lot involved in that. All of them are somewhat related. Then rebalancing delays. You might need to patch your application or your Kubernetes cluster. There's many reasons when the rebalancing will take place. And that will take longer the more state you need to move from A to B. So also longer recovery. If there's any fault or issue with your application, you need to restart, repopulate, and state restore. Same topic, everything will take longer the more state you need. And why would you keep state that you actually don't need for your actual use case or to fulfill your functional requirements any longer? Also operational overhead. When you want to debug, troubleshoot, there's also compaction in RocksDB. You might need to migrate data if you have a breaking schema change. So again, more state, more complexity, and yeah, we want to avoid that. So coming on to data expiration requirements, one requirement is to have, like I stated, dynamic expiry rules, so not just based on a specific time, but also a criteria like the completion of your parcel delivery when it's either delivered successfully or returned to the sender. We want to customize that TTL and also the cleanup interval. Do we need to clean up every minute, every hour, once per day? And we want to have that mechanism to be efficient. Of course, we are engineers, so yeah. And also, if you have a use case like the airport departure board, it's not totally real-time critical with the NFR. If you're within minutes, might be fine, but you might have other use cases where you cannot breach a certain latency you want to or you need to fulfill when processing your stream application. We'll get back to that later. Yeah. Which brings us to getting actually started with presenting 8 patterns how you can achieve a TTL with Kafka Streams. Like I mentioned, there's no out-of-the-box solution with Kafka Streams other than windowing, which is not the same, works for some requirements, but not for all of them and not that customizable. Before we start off, just some fundamentals. I'm not sure who's worked with Kafka Streams heavily or not, but just to repeat some of the core fundamentals we're going to use in the patterns. First is the processor API. So everything Kafka Streams, DSL, is actually implemented on top of the processor API. So if you do filter, map, split, joins, aggregates, anything under the hood is using the processor API, but you can also write your own custom processor. So this is what the interface looks like. There's mainly one method, process, which accepts a single record, and you can do whatever you need to. And there's the init method, where you can get access to the processor context. Processor API provides maximum flexibility, such as access to state stores, or scheduling a punctuator, which we're also going to use. You can also manually forward or commit your records and offsets. Next, state stores. Everything state in Kafka Streams is always using a state store under the hood. But you can also write or define your own custom state stores, or you can customize how you want state to be materialized. There's different store variants, like key value window, or also session windows stores. And we are particularly interested in the key value stores today, and those also come with different types. The default, if you do not specify anything different, is a persistent store, which is RocksDB under the hood, which persists your data to disk. But there's also an in-memory state store. And there's also less commonly known something LRU cache, so the last recently used cache, also one of the patterns we will see in a few minutes. And last but not least, punctuator. Punctuator is almost like a simple method interface, so you usually just use it as a lambda. And you can execute periodic tasks within processors, and you can schedule that based on either stream time or on wall clock time. And you also have access to the processor context. With that, you have access to state stores and can also emit events. One last bit before we start with the patterns, just on the notation. I think I will not go into much detail. I hope a lot of the diagrams are self-explanatory, but just the most crucial parts. The blue box is a topology. The purple box is everything that's kind of within a certain custom processor's context. And yeah, I think to save time, I will just move ahead and start with our first pattern. For the first one, just take a minute for everyone to just take a look at the diagram. But yeah, starting at the left-hand side, we have a source topic. We consume that as a stream. And then we have our custom processor, which also works with the state store and punctuator. And that's all we need as that first simple pattern, where we just consume our topic, and then we simply write our entries to the state store. And in addition, we have a punctuator schedule, which runs every 10 minutes. And what it's doing is simply to just query your state store for all entries, and then just iterate. And we apply our predicate to determine if a certain record we are just looking at can be evicted or not, if it's outdated. If it's outdated, we simply call store.delete and delete the actual record from the store. And that's kind of the TTL fulfilled. How that looks like, here's the custom state store we define with the streams builder. Here's the topology. We just say stream process with our custom processor and the state store name. And I skipped the process part where we just store records. And in the init, just to highlight, here we get access to the state store. Then we have context.schedule. Here, every 10 seconds, that punctuator will run. And we just flush the store, we iterate, and then we, in the end, just delete all of our expired records. That's the basics of the first pattern. Yeah, let's move on and see what else we can do and why this will not work for all of our use cases. Pattern number 2 is quite similar, and it's actually the exact pattern that's also you can also find on the Confluent website when you search for TTL. The main difference is here we do not have a custom state store, but we actually use a k-table. The k-table is stateful by nature, so it also uses a state store under the hood. And we won't touch this state store at all. So whatever our actual business logic is about, we do something useful with the table, join with other streams, or whatever we need to do. But in addition, we simply just define of this K table an additional stream and a custom processor, and essentially almost the same as in pattern 1. We just store records to a custom state store, and we have a punctuator which processes and reads from the state store and iterates, and in the end, if we want to evict data, it emits a tombstone to the actual source topic. So data that expired, we just send the tombstone, and the K table will automatically delete this from its internal state store. And also then, same, our custom processor will also delete the record, and we have our data evicted. One of the differences is actually in this state store, it's a lot more lightweight. We do not need to store the entire value. We can just determine what is our TTL. So we could just pre-calculate just an epoch timestamp, for example. And what we store here is simply the same key as our main record. And as the value, we just store only the data we need to determine the eviction criteria. In this case, again, that flight context, after the flight has been departed, we can purge, essentially. So we just store the departure time. Again, here's implementation details. I think I will not go too much into detail. It's pretty similar to before, and there's just not enough time to read through all of the code. Also, just to mention, obviously the slides will be available, the recording will be available, and there's also a GitHub repo referenced at the last slide, where all of the patterns are actually implemented in a simple playground. You can just go there and look at all the examples, even spin it up locally using a Docker Compose and play with it. So moving on to pattern number 3. Pattern number 3 is the first one that's different to the first two, where we use this last recently used cache. So it looks quite similar in that very basic example. We have our topic, a stream, processor, where we just write to our state store. But this state store is not the default, so it's not a RocksDB store, but it's using this LRU cache. It's also locked. And it here I did also draw explicitly the changelog topic, which is kind of that backup mechanism which you would do a state restore on whenever you move or rebalance or restart your streams application. So this LRU cache, the actual class implementation in Kafka Streams is called memory LRU cache, and it's based on a linked hash map with based on access order, and you need to configure it with the maximum capacity. So simple as that, you just say, here's my state store, 10,000 records can fit in, and if you breach that size of the state store, it will just evict the least recently accessed value from the state store. And the benefit, it's a quite complete solution since there's also a callback used by Kafka Streams to then also send a tombstone to the changelog topic, which means the changelog topic is actually also aware that a record was evicted, and whenever you restore state or you restart, also the changelog topic is not growing infinitely, but yeah, it gets purged, and it matches exactly what the state in memory is holding. A bit of an additional detail, I can see it at the very top, and this is why I did draw it here. It's not exactly necessary since that callback and tombstone mechanism is in place, but I will explain it here. For the next pattern, it's more crucial to do. You can also customize the configuration of your changelog topics. A changelog topic by default is compacted, so you will always only keep the latest record of your state, but you can also, in addition, set the retention not only to compact but also to delete based on time. So in this example, just as a fallback, since you should choose this cache size large enough, you can also set, in addition, after 7 days of a record written to the changelog, it should also be just purged by the Kafka brokers. Which leads us, again, to a quick summary. This is how you define that's custom state store. It's using stores.lru map. It's called map here. Since it's a linked hash map, it's a bit, the wording is a bit over the place, but this is this LRU cache. And you define a max cache size here, 10,000. Just bear in mind, this is by streams task. So this is not the total time of your entire state store, but it's for a single stream task, basically on one partition of the data you're processing. And it's in memory. So there are limitations how much state you can actually hold, or you need to pay a lot of money for having a lot of memory assigned. And the entries are also serialized, so it's still stored as bytes. So whenever you access or you iterate over that state store, you always need to deserialize all the data from bytes to, say, for example, your Afro object, or obviously also just strings or long, whatever server you're using. To make it short, I think if you want to use that, you should understand all the implications. You need to know your data, since you just put in an upper boundary of here like 10,000 entries. So you would actually need to know how your data behaves, how much events you will get over the course of days or whatever your context is you're looking at. So you need to choose a sufficient buffer size. But there's always the risk that you lose data if there's any exceptional situations where you get a lot more events than usual. And when you hit the maximum capacity, you start purging data, which you might actually still need. So very careful with that pattern. Still, for the sake of completion, it's one pattern that can be quite useful for use cases like deduplication, where you just want, like for 1 hour, a bit of a buffer to avoid emitting records that did not change in value. Moving on to pattern number 4. If you go to Google and you search like Kafka Streams, RocksDB, TTL, you will quickly find RocksDB documentation saying, hey, RocksDB also supports TTL. Why is Kafka Streams not offering that TTL as a solution of Kafka Streams? Before we answer that, let's just again look at the diagram. It's essentially almost the same as the previous one and the ones before. We have a custom processor, we have our state store, and here we use RocksDB with setting a TTL of 7 days on this diagram. We also should, before I get to that, Kafka Streams has not a native method or anything to set the TTL, but there's a way to configure RocksDB by using the RocksDB config setter. And in this config setter, you would have the option to set. We'll have a code example on the next page. You can set this TTL, and there you go. You would be able to configure RocksDB to use TTL. The main drawback, also mentioned on the next slide, is if data is evicted by RocksDB, there's no feedback to Kafka Streams. So that means Kafka Streams is not aware that RocksDB evicts data and deletes it from the store, meaning without, again here, that same solution using like a time-based retention of compact and delete, your changelog topic would just grow indefinitely. And whenever you would rebalance or restart your pod, you would do a change restore and you would just reinsert all of the data that RocksDB might have already evicted before. So you have data resurrection, and you would still have that infinite growing state. So to not spend too much time with that solution, there's other implications or limitations. RocksDB, the TTL is actually on insertion based. So insertion does not mean not even update based or access based. That means whenever that key is first written to that RocksDB store, that's the timestamp that RocksDB will use for the TTL. So even when you then would kind of do a state restore, you would have a new insertion time at the moment of the state restore. So it would essentially just mess up most of the things. So it's quite hard to really make use of this. Also, it's a non-strict TTL. So only if compaction happens, values are actually deleted. So if you query the store, you might even get expired data, even if you have defined that TTL, since it's just not applied or it's only applied during compaction. And you won't know when that happens, or you would need to put in extra configuration. And RocksDB is not that straightforward to configure. Again, to mitigate data resurrection, you would also need to use that compact delete pattern on the changelog topic. And yeah, that RocksDB config is global. So if you have multiple state stores, which quite often you have, it would apply for all the state stores. So you would need to add your state store names and switch if-else or switch logic in that config setter, which could lead to more problems if you forget to update something. Anyway, I think I would not recommend this pattern, but for the sake of completion, this is what you could do. You could try to implement it, but I've never used that myself. So yeah. Also, here's the example. I think I will quickly skip over. You can follow up after if you're interested. But yeah, in the end, it's just the option set TTL in seconds. That's how it would look like if you would actually want to apply that. So now we have seen 4 patterns, and I want to take a small break to discuss implications when you actually have a very large state to work with. The implications, oh my gosh, are that actually using this punctuation, it's a quite nice pattern, but it's actually pausing your stream processing. So it's not running in the background asynchronously to your usual processing, but it's actually just stopping your regular consumption and processing, which could cause latency spikes. Basically, if the punctuator will take multiple seconds, you're not processing data for those seconds. Whatever your use case is, you might not, or you might breach your NFRs with that. Iterating store entries takes time. Yeah, so you really need to load this all from disk or from memory, whatever. But you need to deserialize all the values, and if you are approaching like millions of records, or even hundreds of millions of records, it will not be finished within a few milliseconds. It will take seconds, or even the larger the state, the longer it takes. So it grows linearly, and if you hit kind of get closer to a minute or even longer, you might even run into timeout issues of the poll duration or other issues. So the bigger the state, just iterating and processing and evicting is actually not going to work, or it will cause many other problems. I just mentioned it. Values also need to be deserialized. So if you're working with protobuf or Afro or bigger values, this will also cost you CPU, memory, garbage collection, and the longer the punctuator run will take. So moving on to more patterns to try to be more efficient. Pattern number 5 is, again, similar setup, processor, punctuator, state stores. But it's the first time we can see 2 state stores being used by one processor. And what we're actually doing to be a bit more clever here is that we get our records in, and we store them in our main state store. Here it's about bookings of flights. So we just store key value as it comes in. But in addition, we also calculate our TTL timestamp, and then we just use a second store where it's called bookings TTL, which is a very lightweight store where we use a trick to just prefix our actual key with a timestamp. And having done that, we can actually, in the punctuator, we do not read from the booking state store, but we read this TTL state store and iterate. And we're not going to use store.all, but we are actually going to use store.range. And using that pattern with the prefixed key, we can just say, give me all the records from the beginning up to like the current timestamp. So you actually just query exactly the data you want to evict. And if you have millions of records and you run this punctuator every minute, you might also always just get like a few thousand entries that you actually need to evict, and you will not iterate over 100 million records just to evict like 1% of them. So this will be a lot more efficient. Also, this state store you're iterating based on has like an empty string value, so it's not heavy on deserialization. And if you determine this needs to be evicted, you just delete it from the main store and also from the TTL store. So this is already going to be a lot better, but there's also some limitations or implications using that pattern. First of all, we have two stores we need to write to, so this is also some degree of extra cost. Yeah, we need to prefix those keys with the timestamp, so we need to pre-calculate the timestamp if you have that pattern with the parcel example, where you might also need to consider the state of the delivery, if it's completed or not. So it's not only time-based. This pattern will not work for you. And also maybe to highlight, if whatever that time you want to delete or evict data based on, if that changes, you cannot just update this TTL entry. You also need to know the previous value to delete from the store, and then write a new updated value prefixed with the new timestamp you want to evict based on. Otherwise, the punctuator will still pick up the first record and evict it early. So yeah, limitations here as well. Again, the implementation, I think I will skip due to, otherwise I will not finish with my slides. Pattern number 6, I think it's not an actual pattern. I've still found a part of it quite interesting, so I thought I would include it and share. It's mainly using a lazy value deserializer, and it's just addressing that part if you might have a big value. Deserialization is costing computation and all of that. And if you iterate millions of records and you're actually not going to use the key but still deserialize, it's just wasted computation and effort. So if you have a key which actually has a timestamp embedded, here for an example, ULID or the UUID version 7, and you only need that timestamp of the key, why would you deserialize all your data, all your values, if you're not going to read anything out of the value? This is just, yeah, everything really on that pattern. I just found it interesting. It will be quite rare, so if you would ever be able to use that this pattern, it's not very likely. But here's the code. You might find it useful for something else, for other use cases. Yeah, just essentially storing the raw data as bytes, and only if you really need to access that value and invoke a get on the value, then you will actually deserialize. Moving on to pattern number 7. This is the first pattern which is not only using Kafka Streams and not doing this within the topology, but what we are doing here is actually we use a separate job for the TTL. So in this example, we just have a K table which has materialized state. So we have an underlying state store, and the state store by default is logged, meaning we have a changelog topic. And the pattern used here is simply we just use a separate, I just call it job. It's just a process. So it's not Kafka Streams, it's just a regular consumer and producer that consumes from that changelog topic. And we do similar patterns like before. We just consume, we use our predicate to identify which data can be evicted. And for all of those records we can evict, we just publish a tombstone to the source topic, which leads to the deletion from the K table, and we have that fulfilled. The benefit, obviously, is that our stream processing does not use any punctuators, so it's not aware of this, and it also does not need to stop processing. So here it's a true pattern to do that asynchronously in the background. And yeah, quick implementation details. Then we will also discuss again what the implications are with these patterns, or what you need to be cautious of. Implementation also again provided on the GitHub repo. It's we start off just to get all the partitions. of the changelog topic. For each partition, we read our log and offsets, and then we start consuming and processing. So this is kind of here part number 3, and the next slide will expand that portion further. And here we then simply start a while loop, and we pull records from the consumer. We do our predicate. When expired, we send tombstones, and we just continue polling and processing until we reach that log and offset that we read when starting this job. So the job will actually terminate when it reaches these offsets, and it will finish, and you can just reschedule that with whatever cron functionality later, and just run it next time to do another eviction run. Yeah, things to be cautious of here is, well, a changelog topic, it's not actually like an official interface you should interact with. It's an internal topic used by Kafka Streams, so it's kind of an anti-pattern that you start fiddling or consuming that data. It's used to back up the state store, but usually you do not do anything custom with this changelog topic. So yeah, you should be aware that that's not exactly like an official supported way to fiddle with a changelog topic. Yeah, if you would publish large number of tombstones, like 50 million tombstones in a short time span, you might still cause latency on your actual stream process, since it will then process those tombstones and not do the actual processing of the other events. So you could throttle or whatever, but yeah. And I think this is one of the most, it's not critical, most of the time it might not be a problem, but be cautious. While a changelog topic is compacted, compaction does not happen instantly. So the brokers will only compact if there's a certain dirty ratio reached, or after like a minimum time span or a maximum time span, it will do the compaction. But if you actually process the changelog topic, you might see multiple records for the same key with different states of your value. And this could cause unexpected surprises, so you should be cautious. That could lead to reading like an outdated value to determine if you want to expire data or not. And yeah, last but not least, it's a separate job, so more moving parts to maintain, to monitor, and to operate. It's not all contained within your main application. Okay, there's still a bit of time. Last pattern number 8. Here, I would like to thank Adam Sukier, a solution architect for Confluent, who pointed this out after reviewing my slides. It's quite close to pattern number 1. Simple setup, processing, state store, punctuator. But the main difference, instead of just doing store.all and process all of our entries, we actually work with store.range, and we also time box our punctuator. Meaning if you have a very large state and to process all your records, it would take 10 minutes. If we just say we cut off the processing after 10 seconds, and we then just remember the key we last processed, the next punctuator run can just continue using this range query by the last key used. And essentially you would just kind of split this huge state store processing into multiple batches, and eventually, based on your state size, you will reach the end, and the next round will just start from the beginning again. So you can avoid this huge impact on latency or increasing timeouts when processing with the punctuator by just limiting. It can run only 10 seconds, and then we continue processing. Again, implementation detail. I think we do not have time to read through that. This actually leads to a summary. Again, take it with a pinch of salt. This is my own evaluation of all the patterns. So whatever your use case or what you need to do, yeah, you should understand the patterns used. You should evaluate, analyze, and test your use case and what you could use of those. That's the end of my talk. Thanks for the attention. And again, here's some of the links provided at the very bottom That's a link to the GitHub repo where for all the 8 patterns there's working code.